it away. Ooh, see?
Okay. Well, good evening, everybody. My name is Taury Smith. I'm a geologist. I'm currently a consultant. I am formerly the state geologist of New York. So I've come here my whole life. I am Lang Smith's son, who is here joining us tonight. And I've been a geologist for 30 years, but I never really got all that interested in the local geology until last year. I offered to do a talk on the geology of Islesboro, and I thought, oh, I'll pop up there 3 days beforehand. I'll go take a few pictures. I'll look at the map, and I'll pull together a nice story. And I quickly realized that there were a lot of issues with the map, and that there was a lot of actually new work being done here, which I wasn't aware of. And so I got interested. I kind of got hooked. And over the past year, I've been studying the fantastically complex geology of Islesboro and the surrounding islands. And I've actually hooked up with two colleagues, Doug Royce from the University of Maine in Farmington and Justin Strauss from Dartmouth, who had been working out here for years prior to me coming on the scene. And so I've been walking out the outcrops. I've walked out virtually all of northern Islesboro and some of the surrounding islands. And then I've started to make a new map, which I'm going to share with you how I'm going about doing that and what are some of my findings. And some of it I get from the outcrops, which we're very lucky to have all this outcrop, because if you go inland, you don't see nearly that much. But still, there's all the parts in between that are hard to figure out. So I've been using digital elevation maps or LiDAR imaging, which I'll show you. It's pretty neat. And the purpose of the talk is to show you the results of that work and also give you an overview of the geological history of Islesboro. And it really is the ultimate puzzle. How did it all get here? And trying to get clues from here and there, and try to create generate a story that we hope is close to true. Most of the rocks found on Islesboro and the surrounding islands are sedimentary rocks that have been metamorphosed. Let me see if I can minimize everybody. Yeah, there we go. There are also some intrusive igneous pegmatites and basalts, which you will know what that means by the end of the talk, hopefully, that have been metamorphosed as well. There's also significant folding and faulting of the rocks, which makes matters even more challenging. So just some geology 101 here. There are three main types of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are what come out of volcanoes. They form from molten lava or magma from melted rock that cools. And what we have here are basalt, pegmatite, and granite. Then there are sedimentary rocks, and this forms from loose sediment, usually in water, most commonly in marine settings or lake settings or river settings, but also can be blown by the wind. And examples of that here on Islesboro are sandstone, siltstone, shale, limestone, and dolomite, all of which have been metamorphosed, as we call it. They've undergone metamorphism, and metamorphic rocks are rocks under high temperatures and pressures deep in the deep crust and upper mantle. So they've been subjected to some kind of I'm trying to make it so I can see myself, some kind of compression and deep burial that has led to intense heat and pressure. And examples that we see of that here on Islesboro are quartzite, marble, phyllite, slate, schist, and amphibolite. So we got it all here. We've got it all in Islesboro. This is a chart that shows the different grades of metamorphism. So if a rock is buried to a point where it's 150 to 300 degrees C, that we call that low grade metamorphism. And these rock types, these are the original rocks, and then this is what they change to over time. Low grade would be 300 to 450, and we've got some of that here. Medium grade is 450 to 550 degrees C. That's pretty hot. 100 degrees C is boiling. So it's 5 times boiling. That's how hot it got. And we have some of these as well. And so we're going to keep coming back to this chart, as it's pretty helpful to figure out what's happened to these rocks after they were buried. The biggest change and most helpful change is what happens to shale. Shale is a fine-grained rock, and a lot of Islesboro was composed of rocks that were initially shale. And as it's buried and metamorphosed, it first becomes slate, then a rock called phyllite, then schist, and we have a lot of both of these, and then gneiss, which we don't have any of. Gneiss. So you won't have to learn how to say that. But yeah, phyllite and schist are quite common here on Islesboro. We've also got faults, and we got every kind of fault here. We have reverse faults where the hanging wall goes up relative to the footwall, normal faults where the hanging wall goes down relative to the footwall, and strike slip faults where the rocks move beside each other, one side slides along the other, like the San Andreas fault. And here's an example of a little reverse fault where the hanging wall went up relative to the footwall. And that's a nice example. Somebody's unmuted here, and it'd be great if we could get that. I'm going to mute everybody. There we go. And we will continue. Also, it's good to know that all sedimentary rocks, when they're deposited, are horizontal. They're in horizontal layers. Almost nothing on Islesboro is horizontal, and that's because it has been folded. If rocks are subjected to a compressional force, they'll fold like a piece of paper if you push the sides together and they curved up like that. That's what happens to rocks when they're deeply buried and being subjected to a compressional force. And it can get pretty crazy. And I'm afraid a lot of Islesboro, if we could see the whole picture, would look like this. It's pretty complicated what has happened to it. But it all started out looking like this, nice flat layers. And here are some examples from Islesboro of beautiful folds. A lot of you probably recognize that from Turtle Head. These are just classic folds out there. And here's some stuff from the Turtle Head Cove that shows very beautiful folding. And almost all the rocks are vertical or subvertical. And that's because they've all been folded up and gone through a lot of compression over the years. So I'm going to talk a little bit about bedrock geological maps or geologic maps. There is one for all parts of the United States have a geologic bedrock map. Bedrock is the solid rock that is below the soil and loose sediment in a given area. Bedrock geologic maps use colors to represent different rock formations which vary in age and composition, and these can be done at a range of scales. There's the entire United States. And you see some areas are going to have pretty boring maps, right? Because not that much happens, where other areas are intensely deformed. And we are in an intensely deformed area here in Maine that's been through a lot. The more color changes you see, the more complicated it is. And just to illustrate, this is the bedrock here, which is an outcropping. We call that an outcrop when you can see the bedrock, but it's going under the soil and the trees and the houses, and it's actually under the water as well. There's bedrock virtually everywhere under the surface of the earth. If you dig down far enough, you'll reach it. So when we make a map, they commonly don't map the oceans because they have so little information about what's there. So they usually just do the land surface. And this is the very first geologic map ever made of Islesboro. and it was done by a guy named Smith, great name, Smith and others, from 1907. And actually, there's a lot of great stuff on this map, and in some ways it's more accurate than one that was made 90 years later. And the old guys had one thing they had going for them is they knew so little, they had so few ideas about things that they just described what was there. And that is, you'll commonly find that the work done 100 years ago, they'll be a little more accurate about what's actually there because they're just observing and not interpreting as much when they're out there. Then it was redone in 98 by Stewart. And notice this is Islesboro over here, and I've blown it up here. Notice that they both did a very large area, a lot of which is mainly granites and other things. So this is a lot to take in. And I have a feeling there's a lot of good things that are right on this map and a lot of things that I would question that I don't think are right. But he had a lot to do, a lot of different kinds of rocks to work on and age dating and all that. And Islesboro is just a really very difficult, complicated geology. So I'm going to cut him a complete break. And again, there's a lot that's good about this map. And I'll just, as we go along, I'll show you where I differ from what Stewart did. It's good to upfront discuss error, possible sources of error when doing any scientific research. And important to know, science is done by people who have human brains and all that comes with that. And I have learned two things about myself doing this and my own approach. The first is you see what you know, or I see what I know. So I was unfamiliar with some of the rock types when I first started this project, and I initially interpreted them to be something that I'd already seen somewhere else that turned out to be wrong. It took me a while to get used to what I was looking at and realized, oh, this looks like that other thing, but it's not. It's something different that I was unfamiliar with. So I had to learn to recognize that I had that potential for error. And another one is, once I started figuring things out or thinking that I was figuring things out, it's very easy to fall into being model driven. I found out that once I had a model of in my mind of what things should be, it was very hard to see anything other than that. And so I learned I had to go to every outcrop at least twice and to bring other geologists with me to get another pair of eyes on things, because I was very prone to quickly interpreting something and then later finding that it was something different. But I'm feeling pretty good about what I have now, because I've been back several times and brought others out and got their opinion about what we were looking at. And the same thing happens to all scientists to some degree. Over time, the scientific method works these human errors out. So here's what I did: is I walked out all of this coast, pretty much. Anywhere there's a gap up here is an area where there's no outcrop, where I couldn't see an outcrop. The rest, if it's got a color, it is something that I identified. Southern Islesboro, I have not walked out the whole thing yet. I've only gone to the places that are marked. But I feel like I got a sense of what's going on there. And then I've walked out almost all of 700-acre Warren and Spruce Islands as well. So here's what's involved with making a new map. First, becoming familiar with the rock types through observation and reading the existing literature. Walking out the outcrops along the coastline and recording what's there. I already discussed that. Then using LiDAR and other digital elevation maps, such as this one, field observations and geological understanding to try to map faults and to try to figure out what happens between the outcrops. So I know what it is all around the edge of the island, but no idea what happens in between. So this map is actually very helpful for trying to figure out how far layers might extend, where faults might exist, etc. So those are the outcrops that I walked out. And then I used that and used that where I saw, there has to be a change between here because I have this and then I have that. And then looking at the map and from that trying to work out where faults might exist. And you can kind of see there's like a straight line running down here. So I mapped a big fault in there like that. And I knew that these faults had to be in here and I could kind of see these layers changing. And that's kind of how I worked. And so I would not be surprised if some of this is wrong or if I've missed a lot of faults because these are very heavily altered rocks. But it was a first pass. And this digital elevation map, this is actually a shaded relief map of the topography on Islesboro, which is really a neat thing to play around on. So from that, then I made a map where each of these colors represents a different formation with a different age. The green is the Turtle Head Cove formation. This sort of olive color is the Islesboro formation, which is either Proterozoic or Cambrian. We're not sure. Then the yellow is the Hutchins Island quartzite. The blue is the Coombs limestone, and then this purple, which is not seen on this map, is an amphibolite. We know those rocks are between 647 and 1.8 billion years old. And I'll show you how we know that as we go along. So the big changes from Stewart's map were these volcanics don't exist along the edge, nor does that fault. The fault I mapped in is not that different from that, but it's kind of different. I didn't see this fault. And so a lot of the, there's not that much Islesboro, there's no Islesboro formation up in here. There's some over in this area. So you see how different it came out. And then I also extended that down into the 700-acre Spruce Island, Warren Island, Southern Islesboro area to some degree. I'm much more confident down here than I am with all of the rest of Southern Islesboro. But one thing that popped out was how similar Northern Islesboro and that area are with all this yellow and green and blue. And I'm going to walk through that. And these turn out to be the yellow and blue and the purple, there's just a little bit of it, turn out to be very, very old rocks. And Stewart had recognized that. He had mapped these as being Precambrian in age, or Proterozoic, is which that Z stands for. And I changed this part of 700 acre to something else, but I agreed with most of what he mapped in these three islands. So went there to study that, and I learned a lot. And we're going to start with that area. Now here are the ages of the different formations. We've got the amphibolite, which I'll show you, the quartzite, the Coombs limestone, more quartzite. And we know all of these are somewhere between 647 million and 1.7 or 1.8 billion years old. So they're very, very old rocks. They're the oldest rocks in Maine. And they've also seen significantly higher metamorphism than the younger rocks, than both the Turtle Head Cove formation and the Islesboro formation, which I treat separately as it may have been a sort of separate landmass that joined up with these other rocks later on. So we're going to start now with these very old rocks. And that just little bit of purple on the maps is this rock called amphibolite. Amphibolite was an igneous rock, probably a basalt or some kind of igneous rock that was subjected to intense metamorphism. And they're pretty cool looking. Then there's a lot of this very old sandstone there that's called the 700 acre quartzite, 700 acre island quartzite. And it probably formed on an ancient beach somewhere in a time when there were no land plants, no soil, just not much soil to speak of. It's just probably rock and sediment like that is probably what it looked like where that was deposited. Then within that are some beds of garnet mica schist. All the sort of shimmery white looking rock here is a mineral called mica, which a lot of you are probably familiar with. And within that are garnets. These are garnets, which can be gemstones when they're big enough and pretty enough. They can be a nice red color. And what that means that we found amphibolite, so that was basalt that has been metamorphosed to a medium grade. And we also found schist, that mica schist. And the presence of those two things tells us that we've undergone medium grade metamorphism, and the rocks were buried to a temperature where it was between 450 and 550 degrees centigrade. Now it gets hotter as you go down in the earth. The core of the earth is thought to be about 5,000 degrees centigrade. So, but you've got to get down pretty far to get up to 550 degrees C. That would suggest these rocks were buried to as much as 16 kilometers or 10 miles below the surface at some point. And so they've been through a lot. Then this blue layer is the Coombs limestone, or we call it the Coombs limestone. He didn't call it that, but we're pretty sure that we can link that up to Coombs Point, where the Coombs limestone was named. And it's a marble, a beautiful light-colored laminated marble. And what's very interesting there is on Spruce Island. Spruce is this little island right here that you can see from the ferry dock. That point right there, see where it says ZP? That has something called a pegmatite in it. A pegmatite is an igneous intrusion. It came up from a magma chamber and flowed in parallel to the bedding and formed a sill in there of this rock called pegmatite that has very, very coarse crystals. These are all big chunks of feldspar, quartz, and mica. All the sort of black flecks in there are this muscovite mica. And the neat thing about pegmatites, it's not an igneous rock, it's an igneous rock, but they can be age dated. We can get a very accurate date on when that pegmatite formed. And the date they got for that was 647 million years old, which made it the oldest rock in Maine. But the pegmatite is 647 million years old. The Coombs limestone had to already be there in order for the pegmatite to intrude into it. So the Coombs has to be significantly older than 647 because it was deposited and buried to a depth where a pegmatite would form. It was buried to probably 10 miles of depth and then uplifted before the pegmatite was formed. So I'm pretty comfortable saying that these rocks are probably more than 1 billion years old, the Coombs limestone, the quartzite, and the amphibolite. Now we're going to jump up to Hutchins Island. So that was where the old rocks were first found, was down in this area, eastern 700-acre and Spruce Islands are where they mapped the old rocks. Now, my colleague Doug Roish, the guy from University of Maine, and Justin, been working out here for several years, and they sampled a sandstone there, a quartzite, a rock that was a sandstone that's now a metamorphic rock called a quartzite. And they got, and that's what it looks like in thin section. I took samples and made little slivers of rock that you can look in a microscope. So that's 1 millimeter, and these are all quartz. Oh, that's feldspar, but almost all quartz. It's all fused together into a very hard, solid rock called a quartzite. And Doug sampled that rock and sent it out to be analyzed. And there's a neat way they can get age dates on sandstones. They collect minerals in the sandstone called zircons, which apparently are quite common in sandstones. They're very hard minerals that weather out of granites and then get deposited on a beach somewhere and then hardened into a rock. And what they found with that was that the youngest zircon they found was 1.8 billion years old. They didn't find any younger than that. And you'll see that there are other sandstones in the area that have plenty of younger zircons. So what this gives us is a maximum age. It could have formed here, and only included those zircons. But I think it's probably getting back pretty close to that. But remember, the zircons need to be eroded out of a granite somewhere and then redeposited. So the granite has to form, be uplifted, eroded, before the zircon can then end up in being deposited in a sandstone somewhere. So that's where we get the upper limit of 1.8 billion years. It can't be older than that. And that's what we now, between the pegmatite and this finding, we now say that those rocks are between 647 and 1.8 billion years old, making them the oldest in Maine and perhaps the oldest in the Appalachians all through. We also see the schist out there. That's all the shiny stuff, and that is mica, and that's a mica schist. So that has reached that medium grade of metamorphism that we discussed earlier. And I'd made a thin section of that, which makes this beautiful colors. This is all the mica, and this is a mineral called tourmaline. But that's what a mica schist looks like under the microscope. So what Royce and others just restricted their study to this area. But what I've done with my mapping is show that these older rocks go through in a trend like that, all the way from Coombs Point and Point Comfort, all the way out to Seal Cove. And that the very old rocks outcrop all across that area. So I'm going to show you some outcrop photos from that. I'm going to have to get these people muted. Yeah. We're just going to go through all those outcrops and show you what's there. This is Point Comfort. It's right there. It's just north of Hutchins. Beautiful spot. And there's a big outcrop of sandstone and a rock called conglomerate there. Conglomerate is like a sandstone, but it has pebble-sized clasps in it. So it was formed in a very high energy environment where there were a lot like maybe not too different from a beach in Maine, where we have pebbles like this that form on our beaches. And then so that was north of Hutchins, and then I followed it south of Hutchins across Decker Point and over to these outcrops on the other side of that point. There's the sandstone there, more sandstone, and yet more sandstone at the bluffs. So this Hutchins Island quartzite, or the same as the 700-acre formation quartzite, extends across this point and into the north side of Ryder Cove. It's also on the south side of Ryder Cove. There it is again. This is the sandstone, and there's more of that mica schist outcropping on the south side of Ryder Cove in these very beautiful outcrops here. If we come, there's Ryder Cove, so we've brought it through here. Now this surface right here in Sabbath Day Harbor, this is a stunning beach. one of the fun things about this project is I have seen so many beautiful places on Islesboro, but this is I saw this from a long way off. I said, what is that white outcrop up there? I got up here and it is a quartz vein. Everybody sees these little white lines as it's in a pebble or something, or you see it in the outcrops, you'll see a little bit of white filling a fracture. This one is 15 or 20 feet high. The length of the outcrop, I'm sure it was long, it extends longer, and it looks like that. This is all solid quartz with pieces of rock of the host rock that have fallen into it. And it's about 10 feet thick. So the biggest quartz vein I've ever seen. And that is an indication that there's a fault there. When we see that kind of mineralization, it's really only would form in a fault zone. And that lines up actually with how I am drawing the faults through here. The trajectory of this fault lines right up with how these black lines go across, which are the faults that I've put in there. So, and then on to Seal Cove, and there's the sandstone again. And I was walking, here's Big Tree Beach right here. And I walked around the outcrop and into this little inlet here. And I started banging around in the rocks and I found another pegmatite. This is all very coarse mica and feldspar, just like the one on Spruce Island. I said, wow, that's really good evidence that these are indeed the very old rocks that are at least 647 million years old. And actually, Stewart must have found it as well because he made a tiny little triangle that he called the very, very old rock. So he must have seen that little pegmatite as well, but he didn't connect it up to everything else. He just said, well, some weird thing happened and there's a tiny little triangle of that here. But what I am proposing is that it runs, all the very old rocks run all along this belt here. And I'm pretty sure that's right. I've got good evidence of it. So actually, interestingly, right here, the limestone, there are limestones present on, the Coombs limestone is present on Hutchins and on this Decker Point here, but disappear in here. I guess they're faulted out somehow, but reappears again in Seal Cove, where there was actually a limestone quarry at one point. That the digital elevation map actually picks up that, where they dug the limestone out of the where it's outcropping along the coast there. Gareth Roberts owns this, and she said at one point there was a little village around this quarry, a little cluster of houses here where all the people who mined the limestone lived. And then we'll jump back. So that's the Coombs limestone there. We're going to jump back now and look at it on Hutchins, where it's a fantastic outcrop. What I think are probably ancient stromatolites and thrombolites. Stromatolites and thrombolites are the oldest life forms on Earth. The oldest one that has ever been found looked like, that doesn't look very different, does it? I mean, I think they're very similar looking, these ancient stromatolites. The oldest one they've ever dated was 3.5 billion years old. And these are created by cyanobacteria, by microbacteria, which all of us have over time evolved from, probably. But this is the first record of life on Earth 3.5 billion years ago. If we go out on further north, the Coombs limestone was named for Coombs Point. And there's some crazy brecciation and fracturing and mixing and destruction of the rock there. That has the sandstone mixed up with the limestone. And that's another indication that there's a lot of faulting going through here when it's all, the rock is all tortured like that. That's my field assistant there, Max, for scale on that photo. And then again, we see that same stuff we saw out on where the pegmatite was, that light colored rock with the beautiful laminations in it, the stromatolite facies. Outcropping there on Coombs Point. And in some cases, it gets really metamorphosed and looks like a psychedelic dream of some kind. And they're very cool rocks. If we jump further to Warren Landing, the Coombs limestone outcrops again. And this is where we're going to have our field trip on July 17th, is out to that point right there. That used to be an old steamship landing for steamships coming from Belfast. And that's got a lot of really neat mineralization, and it's been through a lot as well. That's what it looks like in thin section. These are all calcite crystals that are all interlocked with each other. And marble is calcium carbonate, and which is what makes lime. And therefore, that's why they mine it. They mined it for the lime so they could make cement with it. And there's an old quarry there on the and an old lime kiln apparently there at Warren Landing as well. And there's the and we jump further north to this point. There it is again, the beautiful gray laminated stromatolite facies, with again more evidence of intense faulting and mineralization. So that's one of the reasons we put these faults through here. The other reason is these green rocks are much younger than the blue rocks, and so the blue rocks had to be pushed up over them by a series of faults, and we're going to get to that in a little bit. Now we'll jump to the intermediate age rocks, which is the Islesboro Formation. It could be either Cambrian or Proterozoic. We just don't have any good age dates on it. But that's what it looks like. And it outcrops all in this area, all down at the ferry dock. You probably, this photo is from the ferry dock from Grindle Point. And you also see it at Pendleton Point. And so it's always very thinly bedded or laminated with lots of different rock types interlaminated with each other. And see the different colors in here. We got tans and reds and grays and blues and greens, and it's very common to see it like that. I walked out in Dark Harbor Pool at low tide and found this really beautiful slaty cleavage there in one of the rocks. That where it got fractured ended up making this sort of crazy pattern, but I just loved how that looked. One of these is the bedding of the rock, and the other is where the fractures kind of reoriented and made cleavage in the rock, so it's very hard to tell which is which. All these tan layers in here are what Stewart called the Islesboro limestone. You see them all through here. And they're almost all these orange beds, which aren't limestone at all, in fact. They're dolomite. There's my very regal looking dog for scale. But they are harder than a lot of the rest of the Islesboro Formation. So they tend to make up some of the cliffs and hold up the eastern edge of the island and prevent it from being eroded by the waves coming in, because these are harder to erode than the gray rocks are. That's what some of that looks like, and I have a thin section of that. This blue mineral here is dolomite. There's no calcite in this at all, so limestone is not really the right word for it. It's better the Islesboro dolomites, these orange beds. And the light colored mineral is quartz, so there's plenty of quartz silt in there. And these little things are micas. So there's a little bit of detrital mica in that rock. Now the Islesboro Formation is commonly cut by these basalt dikes, which is again an igneous rock. It was molten lava when it cut into this fissure in the rock and then solidified there and became part of the bedrock. And they're all over the place. You'll see them at the ferry dock, at Pendleton Point, in almost all the rocks except for the Turtlehead Cove Formation. And again, they form in what we call dikes, which are vertical, where they cut across the bedding, or sills, which run parallel to the bedding in a rock. And you commonly see little air bubbles in them, which we call vesicles, or which were the gas bubbles that were in the basalt that ended up hardening around the gas bubbles in the basalt rock, which leaves this vesicular basalt fabric. And here's from actually my beach in front of our house that we have some beautiful basalt dikes. This is marble and that's basalt there, marble and basalt. And they're very discontinuous, these basalt bodies. I noticed that they also make up a lot of the ledges inland. And oh great, here's an outcrop. Almost all of them were these basalts, which are a little harder than the other rocks. Basalt forms in places like Hawaii. That's what's forming there. It makes the black sand. Or this is Iceland, which is maybe a better analogy. This is all basalt forming in Iceland. And there was a time, all these rocks in purple and red are almost entirely composed of basalt that had flooded out onto the surface, just like it does in Iceland. And so there was a time when all of this was just a field of fire everywhere. All these rocks that are purple and red had extrusive basalts forming on them. But on Islesboro, all we find are the dikes and sills. So what we think happened is the dikes and the sills came up through the old rocks. We see it in the Coombs limestone and the sands and the Hutchins Island quartzite. Also see it all through the Islesboro Formation. And then it flooded out in places like Castine and North Haven. But then the Turtlehead Cove Formation, which is our youngest interval, the green on the map, doesn't have any of those dikes and sills. And that's one of the ways we know it's the youngest, but we have other ways of learning that, but it doesn't have the same dikes, basalt dikes and sills that the older rocks do. So we'll look at that Turtlehead Cove Formation, because this is very different. This is something that Stewart didn't map at all. He called all the Turtlehead Cove stuff Islesboro Formation, but it's very clearly younger and of a different origin than the Islesboro Formation. So this is out on Turtlehead Point, all in the northern Islesboro, and this is what I've been able to work out. It goes from multicolored shale to black shale to green, back to black with a big sandstone bed in it. Then it sort of coarsens up to siltier and then very fine sandy beds that are interbedded with shale. And all of that has been lightly metamorphosed to phyllite, the phyllite stage, not to schist, but to phyllite. So that has seen less metamorphism than the older rocks. And again, most of you are probably very familiar with this outcrop out of the tip of Turtlehead. And that is where it's coarsened up to the siltier or sandier beds interbedded with the shale. So this would be sandstone, siltstone, shale, the black part, sandstone, siltstone, shale. And that is the coarsest and probably youngest part of the formation there that we have. This has been age dated the same way the Hutchins Island quartzite was age dated. Remember, there the youngest zircon they found there was 1.8 billion years. That's way back here. They find some of those, but they also find them all through all these younger ages, all the way up to 514 million years old. So that means this gives us a maximum age for the Turtlehead Cove Formation. It has to be younger than 514 million years old, probably significantly younger, because again, the granite has to form, be uplifted and eroded for the zircons to be freed up to end up in the sandstone. So that makes it Cambrian in age, or possibly Ordovician in age. I lean towards Ordovician, so somewhere between 443 and 488 million years old. So by far the youngest rocks that we have here. They're the youngest. The Islesboro Formation is either Proterozoic or earliest Cambrian, and those other rocks are clearly, the older rocks are clearly Proterozoic in age. And there's The Turtlehead Cove makes awesome outcrops. They're really, really beautiful. This is on the, if you go to Marshall, to Sprague Beach here, Turtlehead Cove, and walk out at low tide along the left side of it, you come to this. There's a beautiful, very cool natural arch that's in the green phyllite, and then a football-shaped cave that's also very cool. And kind of spaghetti cleavage. The rock fractures in a very interesting way. That same unit that we see here also outcrops over here. So we feel comfortable saying that this Turtlehead Cove extends across that part of Islesboro. It also outcrops in a pit here where they quarry this green rock and use it for driveways and stuff, I guess. It's a shale pit. But this beach, which I call the perfect beach, I just love this place out here, this is all the green phyllite of the Turtlehead Cove formation bounding either side of that beach. And it's quite deformed, even though it's lightly metamorphosed, it's sometimes hard to see the original bedding in it because it's got so much of this what we call cleavage in it. And over on this side, these are quartz veins that are forming in what we call an en echelon pattern where they line up like that. And that's an indication of left lateral strike slip fault movement when we see that sort of en echelon vein formation. This is out in Turtlehead Cove on the other side, and this is sort of some blacker shale with siltier inner beds into the very beautiful folded and fractured rock. And out on this point in Prippet Woods, we walk all the way down to the southern end of that point. It's got this beautiful purple. It doesn't really look purple, but believe me, it's purple, tan and green shale. So all these crazy colors here. So that's all this area up here. But why did I draw it in these areas? Well, I'll tell you. This is one of my better findings. There's an outcrop of what could only really be Turtlehead Cove formation here just next to the limestones of Coombs Point. Right on the beach there is this outcrop, which just doesn't look anything. It's definitely not Coombs limestone. It's definitely not Hutchins Island quartzite. It's definitely not Islesboro formation. It's got the green shales, the tan shales like we just saw here. And so we think that this cove was formed on this very soft Turtlehead Cove formation shale. And we'll zoom in. There's some silty beds that actually look a lot like the stuff at the end of Turtlehead Point, and some really neat cleavage in there. It's just really, really a cool outcrop. I highly recommend it. And so I saw it there in this one outcrop, but why did I extend it all the way through here? Well, I'll tell you. We'll use the digital elevation map, and notice that all these wetlands form here, all the tidal channels, and this is Hutchins, and there's a trail that goes out around all these tidal channels here, and they also occur here in Ryder on the west side of Ryder Cove, and again here, and a little bit there. So I just said, well, maybe all that is forming on this Turtlehead Cove formation, the soft shales that are more easily eroded. And that would make sense. You see where the sandstones and the limestones make the hills and the greater topography like this. But those soft areas are forming on a softer rock, or the low-lying wetland areas. So that's how I came up with that map and putting that green in there. And then I just figured, well, it probably goes in this area as well. And so that's how I put that together. That same Turtlehead Cove formation also outcrops on 700 Acre Island, which was a bit of a surprise. I went in here and I landed at a dock there and I went to have a look. And the first thing I saw, well, I saw it's very different from any Islesboro formation that I've ever seen. It's mapped as Islesboro by Stewart. But here's how I think that one goes. You have the older formations here, the very old rocks, the Proterozoic sandstones. Then I think there's a soft shale layer that makes another swampy interval. Then a very coarse conglomerate. We never saw this up north, but I'll show it to you here. And then the green shale and phyllite, very similar to what we saw up on the northern end of the island, and some dark gray shale. So here's the conglomerate. Again, conglomerate is almost like concrete. It has pebbles in it, much coarser grains that you can see with the naked eye. And it's interbedded with sandstone there, conglomerate, sandstone, conglomerate. And that occurs where I've made this dark band here. That's where the conglomerate is. And we'll see later that forms a ridge that runs, it's like a spine that runs down the middle of 700-acre island. And when we look at the conglomerate at the southern tip, it's got even bigger pebbles in it. They're an inch across or more. They're giant white quartz pebbles, probably weathered out of a quartz vein, not unlike that one we saw in the fault zone in Sabbath Day Harbor. And when things like that erode, they make big quartz pebbles, and that's what this was, just full of these big quartz pebbles. It was quite a surprise to find them. And there it is. There's that spine of higher ground that runs down the middle of 700-acre, and that conglomerate runs all along the side of it. But if we walk around this point here and look at this outcrop here, oh, sorry, I wanted to point out again, this is all swampy in here, just like on Islesboro, not swampy here, not swampy there, swampy. And I think that's the same thing that happened in that other place where the very soft shale makes swampy land, wetlands that form over it because it's more easily eroded than the much harder layers that surround it. And here is the green phyllite and then the darker gray shale that's up on this point, around this point over here. They're really cool outcrops. Let me zoom in on that. There are like tombstones standing there, monuments standing up of the shale like that within some of these shaly beds. And here are some that are out, but you know, in the tidal zone that are still standing up. It's our own little monument valley out there. And this shale continues all down this side, and it's also on that point to the south on 700-acre island. So both the Islesboro and Turtle Head Cove formations have only been metamorphosed to the low grade, because we never see schist, we never see amphibolite. We only see it up to phyllite, the phyllite stage. So what we think happened is those old rocks were deposited, buried to this great depth where they turned into amphibolite and schist, exhumed, they came all the way back up to the surface, got the pegmatites in them and everything. Then the Islesboro formation and later the Turtle Head Cove formation were deposited, and then they were buried again to the phyllite grade of metamorphism. So they've really been through a lot, haven't they? Now there are a few areas where I'm still confused, or I see there's more work to do. And one of them is up here in this area. And actually my beach, I've called it Islesboro Formation here. I'm not totally sure what it is. This is where we live, my beach, our beach, my father's beach here. But this is this is all sandstone up here. This whole thing is a sandstone. It just doesn't look like these sandstones to me. Here's what it looks like. It's still got porosity, which you never see in a really well-developed quartzite. And here's a thin section photograph of that. All the blue is are pores that have been stained. So that's porosity in the rock. And in a high or medium grade metamorphic quartzite, you just would never see those pores. Do you remember how densely cemented the one from Hutchins Island was? these are not like that. So I don't think it's seen the same high grade of metamorphism. Now it is cut by the basalts. So it's older than the Turtle Head Cove because we see the basalts cutting through it. But I think it's something totally different from anything else that we mapped in here. And a candidate for it is a sandstone we looked at down on LaSalle Island. There it is. We thought this was going to be the very old 1.8 billion stuff, but it turned out that the zircons there got all the way up to 620 million years old, or 640, something like that. So they're clearly younger, older than the Turtle Head Cove, but much younger than the Hutchins Island quartzite and the 700-acre island quartzites. So I think that part of Islesboro is a candidate to be related to that LaSalle Island sandstone. But I'd like to get some, we never have age dated this, and I'd like to get some samples run for that, for the zircon age dating, and also get some sandstones out of the Islesboro formation and see if we can't nail down an age for, or at least a maximum age for that as well. So, as you, these rocks have been through a lot. The oldest rocks, the amphibolite, 700-acre Hutchins Island quartzites, Coombs limestone, were deposited in the shallow sea on the coast of Africa, probably more than 1 billion years ago. They were buried to a temperature of 450 to 550 degrees C and as much as 10 miles of depth, where they were faulted, folded, metamorphosed, and uplifted. Then intruded by that pegmatite 647 million years ago. Then we think the Islesboro Formation was deposited. That rifted away from Africa at that point, and it was intruded by these basalt dikes, which have been age dated at between 512 and 498. That was uplifted and eroded, and the Turtle Head Cove Formation was deposited probably around 475 million years ago. Eventually collided with North America when there was more burial, folding, faulting, and lower grade metamorphism, buried to as much as 12 kilometers, and then uplifted and eroded again, and then glaciated. So I'm going to run you quickly through a plate tectonic animation. But just to give you an idea, that's 560 million years ago. This is what the continents were thought to have looked like. Most of them are in the southern hemisphere on something called Gondwana. And the Islesboro Formation rocks were probably deposited here. We don't really have any sense of where the plates were more than 1 billion years ago. And so it's hard to pin down where the older rocks might have been deposited. But here's where it was just at toward the end of the Proterozoic. Islesboro was almost at the South Pole. Very interesting. Later on, that Turtle Head Cove Formation, the Islesboro block, the land that includes Islesboro, had moved a little further north, and we think that that was deposited there just off the coast of South America. In fact, there are some similarities between that Turtle Head Cove Formation and rocks we see on the west coast of South America, if you can believe it. So what I'm going to do now is quickly jump into this other thing. Can you all see that? Can you see that?
Yes.
Oh, wait. All right. I want to make sure.
We had it, Taury.
Okay. Oh, wait. There it is. Okay, it's running. So the way this animation works is, there's the color code. The red color is mountains, the tan color is land, light blue is shallow seas, darker blue is deep ocean. And the neat thing there, it'll play backwards and go through time backwards. I'm going to drag it in the interest of time. But you see all the plates moving. So up in the left-hand corner are the ages. So this is 70 million years ago, 80, 90, 100, 120, 220. See, this is Pangea, when all the landmass was together. And then it was separated again back then. And we'll go all the way back. This is when the Islesboro Formation was deposited near the South Pole. And we'll keep going back. And if we follow that, where that is as we go back, this is Islesboro. I'm just going to try to track it for you. We're going back in time 600 million years ago. Now that is moving this way. We're actually between Africa and the Caspian region, if you can believe it, the Caspian region in Eastern Europe. And see this mountain belt here. This is probably the mountain belt that all that first burial metamorphism occurred under. And the Islesboro Formation is about right, the Islesboro Island land is about right there. So what I'm going to do is take you through what happened from that point. I can play God and move the plates. So remember, Islesboro's here. So let's just follow what happens to that as we go through the Cambrian. There it is, moving north. Now it's a little string of islands that are moving toward North America. And then boom, it collides with North America sometime in the Silurian, 440, 420, 400 million years ago, something like that. And then eventually, all this collides and a huge mountain belt grew up there, probably as big as the Himalayas, occurred right off to the east, just off to the east. But that's when all the formations got buried again. And then we rifted apart from Africa and went on through geologic time. And now this is fun. Watch how India moves to form the Himalayas. Ready? Here's India right there. We're going to go boom, boom. Look how it's crunching the land up there. And that's why those mountains are so high today. But that's a neat little thing. So I'll just, we're now at, it's now 8:10, so I've spoken for about an hour. Are you done? I have a few more slides I could do if people want to see them, or I can just wrap it from here. What would you prefer? It'll take another 10 minutes.
We could go another 10, Tori, I think. It's fascinating.
Okay.
And then we'll open it up for some questions.
Absolutely, keep going.
Okay, good. All right, well, these are just some neat visualizations of what the plates might have looked like at different times. So the ages are down here in the left-hand corner. See the 550? So there's, and
Corey, you're still on the video. You need to lose the video.
Okay. All right. Oh, good. Yeah. I'm glad that you pointed that out. It must have been.
There we go.
Wondering what the heck I was talking about. There we go. So these are the ages down here, 550 million years ago. You see, Maine's not there yet. Maine doesn't exist because it has yet to be added on to North America. But you can see the outlines of all the other states there. So it rifted away. Then an island arc came in and collided with North America, but that was not Maine yet. Here, Maine, Islesboro, or the Islesboro part of Maine is coming in this little cluster of islands. So we see then that collides about 400 million years ago. They collided with North America. See this mountain belt that's forming. And then the collision continued, and now it's just incredible mountains all up and down where the two plates have collided with each other. This is when the rocks, all of the formations, the old rocks, the Islesboro Formation, the Turtlehead Cove, all got deeply buried at this point and faulted, folded, metamorphosed. Then they were eroded, but at that time, there were probably mountains as big as the Himalayas. That's a satellite image of the Himalayas, but the Maine was inland there, and then eventually it broke apart from Africa. And this is 115 million years ago. There was a big waterway that actually cut through the western US there called the Cretaceous Interior Seaway. And then eventually it became kind of what we know it to be today. Until glaciation comes. So there was a point about there were multiple ice ages, but 18,000 years ago, there was probably a mile of ice over Islesboro, maybe more, maybe 2 miles of ice. So the ice sheets came down, and as you can imagine, they did a lot of changing of the landscape. When glaciers move, they scrape up the bedrock, they flatten it out, they scrape it, and they pick up pieces of rock, and they can carry them for hundreds or maybe even thousands of miles, where they eventually drop out either under the ice sheet or in front of the ice sheet. And that's so that the glacier moving over the rocks is what causes these beautiful glacial striations, which you can see at both. This is Pendleton Point, which has fantastic glacial scratching, or at the ferry dock has excellent striations as well. Now, I'm sure you've all noticed these boulders everywhere, and granite boulders on the beaches. There's no granite on Islesboro, so any granite that's here had to be brought by the glacier. Interestingly, any rock that was carried by the glacier will almost always have a flat side on it, and that's where it was scraping along the rock that flattened it out like that. Have a look. These are called glacial erratics. If you see a boulder in the woods, that was probably dropped there by the glacier. This is the biggest glacial erratic ever found in Maine. In Phillips, Maine, look at the size of that thing. But that rock was brought in by the ice sheet. It was not formed there. And finally, a lot of you live on land that probably is getting eroded. And I see people with building up big boulders below the edge of their land. And that's where the coastline is made of glacial clay called the Presumpscot Formation. This all was dropped out at the end of the glaciation, just huge volumes of clay that covered almost all of eastern Maine. And within that, you can see floating boulders and cobbles and pebbles that were dropped by the glacier. And also this blue clay, very commonly found in the Presumpscot. And so that is it. That's all I have. And I should do the thank yous. I'd like to thank Patrick and Amanda for organizing this whole thing, inviting me back, and the IHS for having me back as well. My father, Lang Smith, who helped pay for the thin sections that you saw, and which were key to the whole project, and I thank him very much for that. To all the landowners who allowed me to look around on their beaches, and those who actually weren't home and I looked anyway, thank you to all of you as well. And to my colleagues, Doug and Justin. So with that, I will take any questions that you might have. So yeah, Carrie, well, it's Carrie Thomas is the name, but you'll have to unmute yourself.
Figuring out how to do that. Yeah, I have a question. How do you cut your thin sections so that you don't leave striations from the cutting technique?
Well, they have very, very
Geology.
good equipment for that, but sometimes they'll even polish them. But it's not really a problem in any of these rocks. If you get a good company making them, they'll make them without any scratch marks on them. They polish them a little bit, but they're cool. I wish I could have shown more. William.
Hi, Taury.
Hey.
A question, is there still fracturing or movement of the rock formations on Islesboro?
I don't think so, nothing significant. Every time a fault moves, there's an earthquake. So apparently there was an earthquake not too far away from here. I mean, some of them may still be adjusting, probably due to the ice melting more than anything. That actually caused a lot. When the ice sheet was on the land, it actually pushed the land down about 700 feet lower than it is today. And since the ice sheet melted, it's all been rising. And I think that there may be some little tremors related to that glacial rebound.
All right.
Yeah.
When I've gone fishing on McGintycook in years past with Ken Bailey, a famous Maine guide, who passed away a few years ago, there's an island on McGintycook Lake over in the mainland, which has a gigantic erratic, must be 15, 20 feet in diameter. And I used to work with a lot of erratics, so people will understand about erratic.
Yeah, well, we got a few erratics here on the island. I myself included probably, but yeah, they're a great story.
All these people don't have the camera.
So what's interesting, Taury, is that Islesboro seems to be distinct from the rest of North America, so that when we talk about going to America on the ferry, we really are going from one geological formation to a completely separate one. Yes.
Yeah, exactly. Yeah, good. So I just was noticing my friend Jasper has a question. He's written me. Can you unmute Jasper and talk?
Sure. My question is kind of simple. I was just wondering what erosion is.
That's a good question. So erosion is when a rock is out in the rain and the ice and the snow and the waves, and it breaks it apart and breaks it into tiny little pieces. So you'll notice that, like, by an outcrop of rock, you'll see little pieces on the beach that look like that rock. They've been eroded off of that rock. So that was a great question that I probably should have included in the talk. But erosion plays a big role here on the island, right? We basically don't want erosion to happen at too great of a pace here, because that removes the land when it happens. But great question, thank you. Tom McIver has asked, was Islesboro, and you can write
McIver's the guy.
questions in the chat if you wish. Was it part of Avalonia? And what the latest thinking there, Tom, is that it is not part of Avalonia, but part of a separate cluster of microcontinents or islands called Ganderia. And Ganderia were the ones that were thought to have brushed close to the west coast of South America. Let me put that movie back up again, just to show you that how close we came to South America at one point. So remember this, there we are right there. Now look at what this landmass is. When we unfold it, it ends up being the west coast of South America. See that? We brushed right up against this area at one point, and they call that cluster of islands Ganderia.
And the fit.
Gander. That's neat, isn't it?
Continental shelves. It's 90.
So we've got African and South American roots here.
No wonder it's so cosmopolitan.
Okay, I hope people enjoyed it. Oh, Eddie has a question. Since the ages of the rocks differ, does that mean Islesboro was once two separate islands? Well, that's something that thank you for asking. I have been wondering if, remember, the southern Islesboro is almost all that Islesboro formation, and northern Islesboro, or most of it, is either the very old rocks, the Coombs limestone and the Hutchins Island quartzite, or the Turtlehead Cove. I've been wondering if they might have been separate at one point and then were joined together, maybe after the Turtlehead Cove formation, because you never see Turtlehead Cove next to Islesboro. It seems like that was deposited on exposed Coombs limestone and Hutchins Island quartzite, but never on Islesboro formation. So I've been wondering if they were separate, and then some point along that fantastic journey, they got joined up together.
Nancy Alexander, you had a question?
There's a strip of yellow rock on the east side of the Pendleton Point Road that it's very distinct, and it goes from under the Wenner's property straight into the ocean and apparently reappears on the other side of the bay. And it is, I have seen nothing else like it on the island. And
Oh, man, I gotta go check it out now. Well,
Sue Stafford will take you.
when are we going, Nancy? Let's go. See.
Tomorrow.
All right. All right, it's a plan. We'll make
Okay.
a plan for that.
It's a plan, but
Yeah.
I've been fascinated by it. And there's also, we brushed by Scotland at some point, is that right?
Well, when when Pangea formed,
Right.
Scotland was very near to Maine and actually shares some, especially like the New York geology and the Scottish geology are quite similar.
And the same pebbles on the beach. And
Maine was more buried under the big pile that eventually got eroded. But and maybe Western Maine has some of those, some of that stuff.
Well, I don't, there's several people from England and Scotland have mentioned the likeness of the topography and
Yeah,
what
well, it
they
really
knew
does
about
look
the
similar.
geology.
Yeah, it really does look similar. I agree. Yeah, I'll have to learn more about that and have a better answer for you next time.
Shall I call you tomorrow?
That sounds good.
Okay.
All right, good.
Sorry,
Yeah.
sorry.
Yeah.
I had a professor at Franklin Marshall College named Robert Wiebe, and he was doing research in Cape Breton, Nova Scotia, back in the 60s. And he, I believe, was tying in the mountains in Scotland with the mountains in Nova Scotia. And
Yeah,
I don't
that
know.
sounds more like it. Yep.
And it was like the Scots had come over and they saw Nova Scotia and they said, my God, looks like Scotland. And it turns out it was part of Scotland.
That's good. Yeah.
Anybody
Well,
else?
Islesboro, remember, is very different from everything around it. It's very different from the mainland and from North Haven. It's its own thing. We do our own thing here on Island.
Yeah.
So,
better.
This has been really
I sent you my
fabulous.
number, Nancy. So do you,
Okay, I got it.
does anybody else want to have a question?
If
Thank
no one
you.
else has, sorry, did somebody?
Thank you.
Yeah, if no one else has a question, I just want to thank Taury for another fabulous presentation. This is 2 years in a row that he's done just amazing stuff. And watching the level of detail increase as he gets more and more involved with the island is so much fun. Thank you so much, Taury. And
Thank
thank
you,
everybody
Taury.
for coming.
It's been a real joy. The island, I just have been to so many beautiful places that it takes my breath away. And the geology is a gift that keeps on giving, like every day is something new. So it's been really, really fun. I've enjoyed it a lot.
Thank you so
Thank
much.
you.
Good night.
Thank you, Tori.
Thanks, everybody.
Thanks,
We hope to
everybody,
see
and
you. We hope to
feel free
see
to-
you on Tori's tour, on his
Yeah.
walking tour on July 17th.
Yep. That joint
And
you
point.
so much.
we'll see you at the next evening program. Thanks,
you.
everyone.
Everybody.
Thank you.
Thank you.
Bye. Thank you.